Hello everyone, welcome to this lecture. So, in this lecture we will start going into the details of the BGW protocol, the exact details, and we will start with a simple case, namely we will assume a function which just consists of linear gates. So, just to recap, this was the shared circuit evaluation approach proposed by BGW, and all the generic MPC protocol follows this blueprint of shared circuit evaluation, namely it ensures that the inputs are secret shared and all the intermediate values in the computation are also secret shared, and then finally you go and publicly reconstruct the function output. What will be different in different MPC protocols? What exactly is the secret sharing scheme you are following? How exactly the inputs are shared and how exactly the gate invariant is maintained? But the approach or the philosophy remains the same in all the generic MPC protocol. So, the BGW MPC protocols follows the n comma t Samir secret sharing for instantiating this n comma t secret sharing in this blueprint, and the reason it follows it uses n comma t Samir secret sharing is that it ensures that the gate invariant can be maintained without requiring any interaction among the parties. So, remember I said that maintaining this invariant may require interaction among the parties depending upon the type of the gate, because in the arithmetic circuit we can have various types of gates. What I am saying here is that if we use Samir secret sharing to instantiate this n comma t secret sharing, then maintaining this invariant does not require any interaction among the parties if the gate which needs to be evaluated is a linear gate, and this comes from the linearity property of your Samir secret sharing. Okay. So, let us quickly recap the linearity property of n comma t Samir secret sharing. Okay. So, this was your Samir secret sharing algorithm. If S is the value which needs to be secret shared, where S is an element from the field, then the public setup is a finite field whose cardinality is more than n, and the public knowledge of n distinct non-zero evaluation points alpha 1 to alpha n, and these evaluation points will be fixed once for all the instantiations of Samir secret sharing for computing the shares. So, now if S is the value which needs to be Samir secret shared, what we do is we randomly pick a t degree polynomial whose constant term is the value S. That means, the constant term S is fixed, but all other remaining coefficients A1, A2, AT, they are randomly picked from the field. And when I say a polynomial of degree t, that does not mean that AT is not allowed to be 0. I am following the convention that when I say a degree t, that means there are t plus 1 coefficients altogether. The constant term will be the secret, the remaining coefficients can be 0, non-zero, they are any elements from the field. So, even if they are all zeros, altogether I will consider it as a vector of t plus 1 coefficients, and hence a polynomial of degree t. That is the nomenclature I am following here. Also remember that this set P superscript S comma t, it denotes the set of all polynomials of degree t with S as the constant term. Okay. All these things we have discussed rigorously in our earlier lectures, and we know that the number of such polynomials is nothing but the cardinality of field raised to the power t. So, to share the value S, one such polynomial is picked uniformly at random, which is equivalent to saying that pick your coefficients A1 to AT uniformly at random, and the shares are computed by evaluating this polynomial at this evaluation points alpha 1 to alpha n, and ith share will be the evaluation of the polynomial at alpha I. I stress every party will know that the ith share is computed by evaluating this random polynomial at alpha I. That is not a private information because the algorithm is publicly known. It is only the polynomial which is randomly decided by the dealer at the time of secret sharing the value s. So, the linearity property means here the following: if you have a value s which has been secret shared through some random t degree polynomial a, and if there is some public constant c, then each party, if it multiplies its respective share of s with the same value c, each party does it locally, then altogether they will obtain a vector of shares. Together they obtain a vector of shares, I mean each party will have the ith component of that resultant vector, but as a whole I am focusing it, considering it as a vector. That resultant vector will be now n comma t secret sharing of the value c times s. That means without even knowing the value s, just with the knowledge of c, each party can compute its share of c times s. What it has to do? Just go and multiply its share of s with the constant c, that is all. Okay. In the same way, if every party just adds the public constant c to its respective share of s, then each party gets access to its share of c plus s. Okay. And in the same way, if there is another value s prime which has been secret shared by running Samir secret sharing, where the sharing polynomial is say b z, which has been picked from the set of all possible polynomials of degree t with s prime as the constant term. And now, if s I and s I prime are the shares of s and s prime respectively for the party p I, and if every party just goes and adds its respective share of s and s prime, it will obtain its share of s plus s prime, right. So, linearity here means that you can perform linear operations on the secret by performing the similar operation on the shares itself. That means, if you want to compute the shares of c times s, multiply c with the shares of s. If you want to compute shares of c plus s, add the value c to the shares of s. If you want to compute the shares of s and s plus s prime, add the shares of s and s prime. Okay. So, now with this observation, we will go and see the BGW MPC protocol for the simple case where the function that the parties want to compute is a linear function. And again, there are plenty of real world examples, real world computations which can be abstracted by linear functions itself. So, the setting here is the following. So, this is the theorem statement that I am quoting from the BGW paper. You have the set of parties which I denote by this fancy p, and we are in the private channel model, and assume that there is a publicly known function f over the field which is a linear function. That means, it takes the inputs x 1, x 2, x I, x n from the respective parties, and the output is c 1 times x 1 plus c 2 times x 2 plus c n times x n, where c 1, c 2, c n are publicly known constants. So, c 1, c 2, c n, they are publicly known constants, publicly known constants from f, because this is the form of any linear function over the field. So, for instance, if I take n is equal to 4, then the inputs are x 1, x 2, x 3, x 4, and this is the corresponding arithmetic circuit. Okay. So, as I said, there can be several real world functions which can fall under this category. So, if you remember the toy summation protocol, the summation protocol is basically a linear function because your constant c 1, c 2, c n are 1 all. Okay. So, like that there are several interesting linear functions which the parties may want to securely compute. Now, what the BGW theorem says here for the linear functions is the following: if you are in the private channel model, and if there is a semi honest adversary controlling any set of t parties, where t of course has to be strictly less than n, then still there exists a secure MPC protocol for computing this function y, and this holds even if the T corrupt parties are computationally unbounded. Okay. So, we are now going to see the proof of this theorem. The proof of this theorem will be through a protocol, and then we will analyze the security of this protocol. And now, if you are wondering why t less than n, because if I say t is equal to n, then basically if all the n parties are corrupt, then all the inputs are revealed here. Okay. So, that is why the trivial bound for t is t should be strictly less than n. And again, what we are going to do is we will see the BGW shared circuit evaluation for securely evaluating this function. So, for demonstration purpose, I stick to the case where n is equal to 4, but whatever I am discussing here, it generalizes for any n which is greater than t. Okay. So, this is the circuit which parties want to securely compute. So, what the first party does is the following. So, remember the first stage in the shared circuit evaluation is approach is the inputs, respective inputs of the parties for the function needs to be secret shared, and who should secret share those inputs? The input owners themselves. So, P1 is the owner of the value x1, it will run an instance of n comma t Samir secret sharing, where the parameter t is also publicly known. Let us make t is equal to 2 again for the sake of demonstration. So, it will pick a t degree, namely a t degree polynomial whose constant term is x1, and compute the vector of this shares x1, x2, x1 2, x1 n. In this case n is 4, so it will compute 4 shares, and it will distribute the respective shares to the respective parties. So, it keeps x11 itself, it gives x12 over the secure channel to P2, it gives x13 over the secure channel to P3, and it gives x14 over the secure channel to P4. Okay. So, that means now each party, what information regarding x1 they have respectively, each party now have their respective shares of x1 in their local copy of the circuit. Now, in parallel, party P2 will act as a dealer and secret share its input x2 with the threshold t equal to 2. Okay. So, it will compute a vector of 4 shares, it will keep the share x22 with itself, and the first share of x2 it will give over the secure channel to P1 and so on. And now, each party they have got one share of x2 corresponding to they got one share of x2. And remember, all the evaluations are performed over the same alpha 1, alpha 2, alpha n. That means, the alpha 1 to alpha n which are used by P1 to compute the shares will be the same as which are used. So, P2 also will use the same set of alpha 1 to alpha n, P3 also will use the same set of alpha 1 to alpha and so on. So, alpha 1 to alpha n they are not going to change, and that is why I am not bringing them into picture. In parallel, P3 will independently secret share its input as per Samir secret sharing, and now everyone will have their respective shares of x3. And P4 will independently generate Samir shares for the input x4 and distribute among the parties. Now, before I proceed, let me stress here that remember, Samir secret sharing is a randomized algorithm. That means, even if the parties P1, P2, P3, P4 executes this BGW MPC protocol with the same value of x1, x2, x4 and x3, the shares which are going to be produced in every instance will be different, because they depend upon the internal randomness, namely the sharing polynomials which are used to compute the shares. And it will not be the case that for sharing the same xi every time the same sharing polynomial will be picked. The coefficients of the sharing polynomial they are picked uniformly at random. So, that is why, since the sharing polynomial could be picked uniformly at random, the shares themselves are going to take different values depending upon what precisely are those random coefficients. Okay. So, this completes the input stage. All the inputs are now available in an n comma t secret shared fashion. Now, the parties will proceed to evaluate the gates. And what are the gates in this circuit here? If you see closely here, all these gates are linear gates. So, this gate is a multiplication gate, but multiplication with a public constant C 1. This second gate is also a multiplication gate, but it is a linear gate because C 2 is publicly known constant and so on. And after that there is a plus gate which anyhow is a linear gate, right. So, remember your computations which parties want to compute is y is equal to C 1 times x 1 plus C 2 times x 2 plus C 3 times x 3 plus C 4 times x 4. This is the computation which parties want to securely compute. X 1, x 2, x 3, x 4, no one knows their values right now, they are collectively secret shared, and since this is a linear function of x 1, x 2, x 3, x 4, by the linearity property of Samir secret sharing, if the same linear computation is performed on the shares of x 1, x 2, x 3, x 4, it will result in a shares of y, and that is what the parties will do. Each party will locally compute the same linear function of the shares of x 1, x 2, x 3, x 4, and this they are doing locally. By saying locally, I mean they are not interacting, whatever values they have at their own disposal, they are computing this linear function respectively. And now, after this there is no other gate in the circuit, that means the computation has been performed. Now, it is the time to announce the results. So, everyone announces the result publicly, namely their respective shares of y 1, y 2, y 3 and y 4, they publicly announce, and if they now publicly announce, everyone will now have the full vector of y 1, y 2, y 3, y 4, okay, namely all the shares of y, and now they can apply the Lagrange interpolation on this vector of y shares and get back the value y. Okay. That is a BGW MPC protocol. So, now we have to analyze whether this protocol is secure or not and so on, but before going into that we will first analyze the number of rounds required in the protocol and how much communication is done in the protocol. So, round complexity means the total number of rounds required in the MPC protocol. Communication complexity means how many bits are communicated in the protocol overall. Okay. And remember, by round I mean the following: one round means compute something, send those values, and whatever the parties have sent in that round, receive them. That finishes one round. Next round, process whatever messages you have received in the previous round as per the protocol, and then decide what to send in this round, send those messages, and other parties are also doing the same. So, they will be sending something, receive those values, and then round ends. So, like that we have to count how many such send, receive, compute are performed by the parties in this BGW protocol, assuming that the parties want to securely compute the linear function of n inputs. Okay. So, where exactly interaction is needed in the BGW MPC protocol? The interaction is needed for secret sharing the inputs of the parties, right. So, the first step of the protocol was each party acted as a dealer and distributed shares for its respective input. So, for that interaction is needed over the secure channel, right. If I want to implement this protocol, by interaction I mean, say I have to open the SSH socket or SSL socket, and then I have to communicate my shares to the respective receiver over those channels. So, how many times I have to basically open the channel and communicate, that is what I am now trying to compute here. So, interaction is needed for sharing the inputs, and this can be completed in one round. Even though when I demonstrated the protocol, I first demonstrated that P1 shares and then followed by P2 and then followed by P3 and then followed by P4, but when you are implementing it, when P1 is secret sharing its input At the same time P2 also can start its secret sharing instance, because there is no dependency between P2 sharing its input and P1 sharing its input, because the sharing polynomials which P1 and P2 pick respectively, they are independent. So, when P1 is sending its share, at the same time P2 also can start sending its shares, because the channels are independent here, right. So, that is why overall it will require one round of communication. It will not be the case that the sharing is happening here in a sequential fashion, no, the sharing is happening in parallel. So, that is why it requires one round. And how much communication happens if I count all the instances of sharing here. So, there are n instances of secret sharing, and for each instance of secret sharing, order of n values or field elements have to be communicated. Each one field element has to be communicated to every other party, because that is a share. So, for one instance of secret sharing, n field elements are communicated. For the second sharing instance, n field elements are communicated. For the ith sharing instance, n field elements are communicated, and for the last sharing instance, n field elements are communicated. So, overall n square field elements are communicated, order of n square field elements are communicated. Of course, a party keeping its share of its own input to itself will not be considered as a communication, but in the order notation, in terms of order notation, the overall communication that is happening is order of n square. So, these many field elements are communicated, and each field element can be represented by these many bits. Namely, there are these many number of field elements, and each field element can be represented by log of the number of elements in the field. So, since n square such field elements have to be communicated throughout, the communication needed for the sharing protocol, sharing part is this much. Now, where else is the interaction needed in the BGW protocol if the function that needs to be communicated is a linear function? Well, the shares of y, they are computed locally, that does not demand any interaction among the parties. But then to learn the function output, the value y, the shares of y needs to be made public. Okay, everyone has to announce the share yi. So, if pi is the ith party, it has to announce the share yi to every other party. Okay. If it will be sufficient if any t plus 1 of these n parties make their respective shares of y public, but in the worst case my t could be all the way n minus 1, that means I may need all the n shares. So, that is why when I am explaining here I will say that okay, all the n shares need to be public, but any t plus 1 shares are sufficient if they are made public. So, there are two approaches here. One approach could be that in a single round every party send its respective share of y to every other party. So, this will require order 1, this will require single round and quadratic in the number of parties communication. Alternately, I can do the following, a modified reconstruction. Instead of one round, if you are willing to give me one additional round of communication, but ask me to save the communication, I can do the following. In the one round approach, every party sends its share of y to every other party. So, that is why single round, but n square communication, of course, n square log of f times bits. But if you give me two rounds, then what I can do is the following. Let all the parties agree on a predetermined party as per the protocol itself. It could be any predetermined party, any designated party, let it be the first party for simplicity. Then in the first round every party sends their respective share of y only to that designated party. So, that will require one round and order n communication in terms of field elements. That single party, now it will have all the shares of y at the end of the first round. So, it can reconstruct y, and now in the second round it goes and announces the result y to everyone. So, that will be the second round, And how much communication happens in the first round? It is order n, again in terms of field elements. How much communication happens in the second round? Again a single field element, which is order n. So, overall order n times log of f bits are communicated. So, there is a trade off here. If your network is kind of very slow, where you cannot afford to communicate multiple times among the parties, then go for this one round approach. That means, if the bandwidth is not an issue, but in number of times the parties need to open the socket and interact is the issue, then go for this one round approach. But if the bandwidth is the issue, but the network is stable and you can communicate as many times as possible, but the restriction is that every time you are given a restriction that your bandwidth is very small, then go for this two round approach. So, depending upon what is your primary constraint, whether it is a number of times you want to interact, whether it is a number of times you want to interact is more critical, or whether it is how much you want to communicate every time, that is critical. You decide whether you want to go for this one round reconstruction approach, or whether you want to go for this two round reconstruction approach. Okay. So, these are the references used for discussing today's lecture. We have not yet seen the security analysis. We have seen only the protocol details for computing the linear function, and we have analyzed the round and communication complexity. Thank you.